Peru just got hit twice. 2 earthquakes, 2 moments when the ground suddenly moved beneath one of the most earthquake-prone regions on Earth. And then came the number that changed the story, 7.2. A magnitude? 7.2 earthquake is not an ordinary event. It represents an enormous release of energy beneath the Earth's surface. But here's the part that matters. The number 7.2 doesn't tell us what happens next. It doesn't tell us whether another major earthquake is coming. It doesn't tell us whether the second event was an aftershock. And it certainly doesn't give scientists a countdown clock. To understand what happens next, researchers have to look at something much more complicated. The sequence. Where the earthquakes happened, how far apart they were, how deep they occurred, how the surrounding faults are behaving, and what happens in the hours and days afterward. Because when earthquakes strike twice, the second event can completely change how scientists interpret the first. And that's exactly why Peru's latest earthquake sequence deserves a closer look. Peru is not a stranger to powerful earthquakes. Along the western edge of South America, the Nazca Plate is being forced beneath the South American plate. This process is called subduction, and it is one of the fundamental reasons the region experiences powerful earthquakes. Imagine 2 enormous pieces of Earth's crust interacting over hundreds of kilometers. They don't simply slide past each other smoothly. Parts of the boundary can become locked, stress builds, the rocks deform, and eventually, sections of the crust can suddenly rupture. That rupture sends seismic waves through the Earth, and those waves are what we experience as an earthquake. This is part of the larger tectonic system surrounding the Pacific Ocean, which is one reason the Pacific margin contains so many major earthquake zones. Knowing that Peru is earthquake-prone doesn't answer the question everyone is asking now. Why does this particular sequence matter? A single earthquake can be relatively straightforward to analyze. Scientists locate it, determine its magnitude, calculate its depth, identify the likely fault mechanism, and compare it with historical activity. But when another earthquake appears, the investigation changes because now scientists have a sequence. And sequences can contain clues that individual earthquakes don't. Imagine watching an earthquake map of Peru. At first, there's one marker, a single event. Scientists determine its location, calculate its magnitude, determine its depth, and begin examining the fault movement that produced it. At that moment, it could still be a single earthquake story. A powerful event occurred, the ground shook, scientists analyze the data, and then they wait. But earthquakes don't always behave like isolated events. Sometimes another earthquake follows, sometimes several do. When that happens, one of the first questions scientists ask is, are these earthquakes connected? That's not as simple as looking at a map and seeing 2 dots. Scientists have to examine the timing, the distance, the depths, the fault orientation, and the overall behavior of the sequence. 2 earthquakes can happen relatively close together without one necessarily being the direct cause of the other, and that's where the second earthquake becomes so important. Now imagine that second earthquake appearing on the map. Event 1, then Event 2. Suddenly, the story has changed. Was the second earthquake an aftershock? Was it triggered by changes in stress from the first earthquake? Did both events occur along the same geological structure, or are they simply 2 earthquakes occurring within the same broad tectonic region? Scientists can't answer those questions from magnitude alone. They need the complete seismic picture. How much time passed between the earthquakes? How far apart were they? Were they at similar depths? Did their fault movements point toward the same structure, and did additional earthquakes follow? There's a major difference between saying 2 earthquakes happened and saying these 2 earthquakes belong to the same sequence. That distinction matters, and it becomes even more important when one of those earthquakes reaches magnitude 7.2. The number sounds simple, 7.2, but magnitude is more complicated than it looks. Magnitude describes the size of an earthquake, and a magnitude 7.2 earthquake is a major seismic event. But magnitude alone doesn't tell you how much damage occurred. It doesn't tell you how strongly every person felt the shaking, and it doesn't tell you exactly how dangerous the earthquake was in every location. Several other factors matter: depth, distance from the epicenter, local ground conditions, building quality, population density, and the duration and characteristics of the shaking. Imagine 2 earthquakes with the same magnitude, where one occurs far from major population centers, and the other occurs close to a densely populated region. The consequences could be dramatically different. That's why scientists don't simply look at the number 7.2 and stop. They want to know where that energy was released. That brings us to one of the most important pieces of the puzzle: depth. An earthquake doesn't happen at the surface. It begins underground, sometimes relatively close to the surface, sometimes much deeper. That depth can dramatically influence how the earthquake is experienced and what scientists learn from it. A shallow earthquake can produce intense shaking close to the epicenter, while a deeper earthquake can distribute its energy differently. Depth also gives researchers information about which part of the Earth's crust or subducting plate may have been involved. When scientists analyze a major earthquake, they're essentially building a 3-dimensional picture. Not just where, but how deep, what direction the fault moved, what geological structure was involved, and perhaps most importantly, what happened around it afterward. After a major earthquake, the surrounding crust doesn't simply return to normal. The stress field has changed, and that can lead to another phase of seismic activity. Think of the Earth's crust as an enormous, constantly moving system. The plates are slowly moving, but the rocks along their boundaries don't always move smoothly. Some sections become locked, stress accumulates, and eventually the rocks can overcome that friction and suddenly slip. That movement releases energy in the form of seismic waves. That's an earthquake. But the rupture doesn't exist in isolation. The surrounding rock has just experienced a major change. The forces acting on nearby structures can be altered. Some areas may experience increased stress, others may experience decreased stress, and some nearby faults may respond with additional earthquakes. This is one reason aftershocks happen. There is an important misconception. Not every earthquake that happens afterward is automatically an aftershock. Scientists have to determine whether the later event actually belongs to the same sequence, and that requires looking at the earthquake pattern. A major earthquake may last only seconds, but the seismic sequence can continue long after the main rupture. Additional earthquakes can occur. Some may be much smaller, others can still be significant, and their frequency often changes over time. Immediately after a major event, earthquakes may occur more frequently. Then, in many sequences, activity gradually declines. This is one of the patterns scientists study. Where are those earthquakes happening? If they're clustering around the original rupture zone, that may fit an expected aftershock pattern. If they're appearing along nearby structures, scientists may investigate whether stress has been redistributed. If they're moving into a different region, researchers want to understand why. This is why an earthquake map becomes so important. Once you put time and location together, a pattern can begin to emerge. Picture a map of Peru. One large marker appears, 7.2. Then smaller markers begin appearing around it, 1, 2, 5, 10, more. Now scientists can ask questions that weren't possible after the first earthquake alone. Are the events clustered? How far from the main rupture are they? Are they becoming deeper or shallower? Are they following a known fault? Are they spreading along the boundary between the tectonic plates? And are they behaving like a typical aftershock sequence? This is where modern earthquake science becomes incredibly powerful. Researchers aren't simply watching dots appear on a screen, they're analyzing thousands of measurements. Seismic waveforms, earthquake locations, depth estimates, fault mechanisms, historical patterns, and the timing of each event. The goal isn't to predict the future with certainty, it's to understand what the Earth is doing right now. Sometimes the pattern itself becomes more interesting than the original earthquake. Is the seismic activity moving? Imagine the first earthquake occurs in one location, and then later earthquakes appear progressively farther along a fault system. That could indicate that the sequence is spreading through the crust. But here's where we need to be careful. A pattern of earthquake migration does not automatically mean a larger earthquake is coming. This is one of the easiest mistakes to make when looking at earthquake maps. Humans are naturally good at connecting dots. We see one event, then another, and our brains immediately search for a story. But scientists need something stronger than visual patterns. They need evidence. They need to know whether the events share a physical connection, whether the timing makes sense, whether the depths are consistent, whether the fault geometry fits, and whether the sequence is behaving differently from what would normally be expected. A map can reveal a pattern, but a pattern doesn't guarantee the future. Could a magnitude 7.2 earthquake trigger another major earthquake? The answer is that it can change the surrounding stress field, but that's very different from saying another major earthquake is guaranteed. When a fault ruptures, the distribution of stress in the surrounding crust changes. In some locations, stress may increase, while in others it may decrease. The amount depends on several factors: the size of the earthquake, the location, the orientation of the fault, the direction of movement, the distance between faults, and the geological structures surrounding the rupture. This is called stress transfer. Scientists can model it and estimate how stress changed in surrounding areas, but they can't simply plug in the number 7.2 and calculate that the next earthquake will happen tomorrow. There is no equation that works like that. A major earthquake can be followed by many smaller earthquakes. A sequence can gradually fade. Sometimes another significant earthquake occurs, and sometimes the surrounding region simply becomes quieter. That's why scientists monitor what happens next instead of announcing a prediction. Because Peru lies along the Pacific coast, another question naturally appears. Could a major earthquake produce a tsunami? The answer depends on what physically happened during the earthquake. A large undersea earthquake can potentially displace the seafloor. That displacement can push a huge volume of water, and that can generate tsunami waves. But not every magnitude 7.2 earthquake produces a tsunami. Magnitude alone isn't enough. Scientists need to know the earthquake's depth, its location, its fault mechanism, whether the seafloor moved vertically, and whether the movement was large enough to disturb the water above it. That's why tsunami assessment is based on physical characteristics of the earthquake, not simply the headline number. So even when people hear magnitude 7.2, there are still several unanswered questions. What moved? Where did it move? How did it move? And what happened afterward? After a major earthquake, scientists don't simply wait for another headline. They watch the data. First, aftershock activity. Are additional earthquakes occurring? How frequently, and are they becoming less frequent? Second, location. Are earthquakes concentrated around the rupture, or are they spreading? Third, depth. Are events occurring at similar depths, or is the distribution changing? Fourth, fault behavior. Which geological structures are involved? And fifth, the overall seismic energy of the sequence. Is the activity behaving roughly as expected, or is there something unusual that requires closer investigation? This doesn't mean scientists have a secret prediction hidden somewhere. It means they are constantly updating their understanding as new information arrives. The story changes as the data changes. So let's separate fact from fear. A magnitude 7.2 earthquake does not automatically mean another magnitude 7 earthquake is coming. It does not mean the entire country is about to experience catastrophic shaking. It does not mean every later earthquake was directly caused by the first one. And it does not give scientists a precise countdown to the next major earthquake. What it does mean is that a major rupture occurred, the surrounding crust has been affected, and scientists now have a new seismic sequence to study. That sequence may produce aftershocks, it may gradually fade, or it may reveal information about how stress is being redistributed through the region. The honest answer is that scientists need time and data, and sometimes uncertainty is the scientifically correct answer. Peru's latest earthquakes are part of something much larger, a planet that is constantly moving. The Nazca Plate continues interacting with the South American plate, stress continues accumulating and being released, faults continue shifting, and earthquakes continue reminding us that Earth's surface isn't actually still. We experience the ground as solid, permanent, and stable, but at geological timescales, it's anything but. The mountains change, the coastline changes, faults move, plates travel, and earthquakes are moments when some of that enormous movement becomes suddenly visible to us. When Peru gets hit twice, the real story isn't simply two numbers appearing on an earthquake app. It's the interaction between two massive pieces of Earth's crust. And scientists are now watching to see how that system responds. Peru just got hit twice, and the magnitude 7.2 tells us that the first event was powerful, but the second earthquake adds another layer to the story. Now, scientists aren't asking only how big the earthquake was, they're asking what the first earthquake changed. Did it produce a normal aftershock sequence? Did nearby faults respond? Did seismic activity migrate? Did the surrounding crust settle into a predictable pattern, or is something about the sequence unusual? Those answers won't come from a single number. They'll come from the earthquakes that follow, the maps, the waveforms, the depths, the fault models, and the data collected over time. After a major earthquake, the Earth doesn't immediately go silent. It keeps moving, it keeps adjusting, and it keeps giving scientists new information. Peru got hit twice, but the second earthquake isn't necessarily a warning of something bigger. It may simply be another part of the Earth's natural adjustment after a major rupture. That distinction matters because the goal isn't to turn every earthquake into a prediction. It's to understand what the planet is telling us. If another major earthquake appears, the question won't simply be how big it is, but what the pattern is telling us. Sometimes the most important part of an earthquake isn't what happened in those few seconds, it's what the Earth does next. If you want the next update without the hype, subscribe and stay with us. We'll follow the data, the sequence, and whatever comes to it.